Well, let me. This is more or less a plan for the talk. Maybe we finish today, or maybe we continue. We do half and half to make it not too long. Um, so, so last time I was explaining that an orbifold is something that locally looks like a quotient. So rather than having one-to-one charts, now orbifolds have many-to-one charts. Let me see if I can write here with this pen here. So a typical orbifold, now a typical chart looks like, yes, an open set in Rn, why not? But the map that in this direction is many to one in such a way that this thing here is, this map is the action by a finite group. And these are the local charts. But gluing these charts can be somewhat confusing, you know. You have a complicated situation, and you have these kind of charts. The intersection gets a little bit tricky. Because now it's not so clear what you mean by the map between the charts. I can get confused, and this is especially so. There is a problem that seems kind of a nitpicking at first, like something silly, but turns out to be quite fundamental. Surprisingly, I think that is that this chart could have a kernel, so to speak, of a subgroup in G that does nothing in U. In fact, it is even conceivable that you have an orbifold that looks like a smooth manifold, and at every point the group does nothing. You see what I mean?
Yes, of course.
And this is extremely interesting case. It's called a G-gerb. This case of an orbifold in which the group does nothing is called a gerb with band G. And already, if the G is abelian, the situation is much easier. But if G is not abelian, even this case is absolutely fascinating. And it's a very interesting kind of orbifold. And it's the kind of orbifold that completely separates the classical geometric orbifold that had singularities where you could read off the group action by a kind of a Galois development of the singularity. A Galois group of the equations of the singularity, with an orbifold where you cannot do that at all. It looks like a smooth manifold, just the space. The information is not, it's an additional piece of information.
Just a question, is it a product? Is it the product of a manifold and the quotient of the point by this group, or it's not?
Not at all. No, not at all. It is. It is. It is something different. It is something. It is a gerb. It's not a product. Locally, it is a product, but a product it is not. So, so if at every point you have the same stabilizer G all over the, and there is an interesting example of this in classical mathematics. Think of the modular space of elliptic curves. Why does this stop writing? I don't know why it stops writing. It didn't stop writing, just got slow writing. Okay. So you get the modular space of elliptic curves. Looks something like this. But remember that every elliptic curve has an involution. You remember that? And then in the real modular space of elliptic curves, every point has a CMOD too. This is often not considered somehow, but it's there, and it should be there for the actual natural modular space of elliptic curves. You see what I mean?
Yes, you mean multiplication by -1
That's
on
right.
everything. Yeah.
That's right. That's right. And it should be there. It should be there. Well, so to deal with this problem, to mathematize in an organized fashion this thing that could get exceedingly confusing, believe me, lots of papers, and I'm not kidding. I know many papers, a few papers, certain papers that are wrong because this is confusing. The idea is to introduce the concept of a Lie groupoid to organize this information. And so an atlas of an orbifold will be a propertal Lie groupoid. This is what an atlas will be. And classical atlases of manifolds are propertal Lie groupoids. Nobody thinks of them like that on a day-to-day basis, but they are the category of atlases on an ordinary manifold is a subcategory of the category of propertal Lie groupoids. And so many groupoids will represent the same orbifolds because there will be various atlases of the same orbifolds. Now, some people call orbifolds the Lin-Montfort stacks. Some people call orbifolds the Lin-Montfort stacks. But the name is very, very long, and I prefer myself the word orbifolds. So we have these propertal Lie groupoids as atlases. So what is a propertal Lie groupoid that will be the atlas of an orbifold? Well, it has the objects, and it has the arrows, the morphisms. It is a category where every arrow has an inverse. It's a groupoid. And for every arrow, well, you have the source of the arrow and the target of the arrow. And there is these two maps. And for a groupoid to be a Lie groupoid, X0 will be smooth manifolds. The set of objects, it will be a small category because objects and morphisms will be sets. So we won't allow these huge categories. They will be a small category. Sometimes it is useful to use a very large, not small category in this theory. But often what you do is you take an equivalent subcategory that is small. But anyway, consider small categories. This is smooth manifold, this is smooth manifold, this is smooth map, this is smooth map. To every object, you assign the identity arrow, and this is a smooth map. To every arrow, you assign the inverse arrow, and this is smooth map. And to a pair of arrows, so that the target of this arrow is equal to the source of this arrow, you assign the composition, the multiplication of the arrows, and this is a smooth map. And moreover, well, these are smooth maps. Now, for it to be an orbifold, I'm going to ask that the maps are proper and étal. And what this will mean in practice is that this is kind of étal will mean that this is kind of a covering map. Namely, if I take a point here, I take a small neighborhood, the inverse of S is a collection of small neighborhoods. The same for the target, and all the maps really. They will be étal. Étal will mean in this C infinity category will just mean that it's a local diffeomorphism or étal. And proper means what proper means, you know. In practice, it means that the inverse image of a point will be finite. I won't have these infinite problems, you know. The inverse image of a point here will be finite, and for every map it behaves like that. So this will ensure that I'm talking about an Orbifold. If I drop the property et al, and I ask only that S and T are subjective submersions, I could change et al for surjective submersion. Then I would get orbifolds where the stabilizers of a point would be, rather than finite groups, would be Lie groups. And they are also important in mathematics. They are called Artin stacks, when the stabilizers are not finite groups, but rather Lie groups. So let me stop there and ask you, is more or less clear what is a proper et al Lie groupoid?
Yes.
Very good, proper et al Lie groupoid.
So only finite groups, right, as stabilizers?
The stabilizers finite groups. The proper
or can it be discrete group, like integers?
The proper condition prohibits discrete.
Okay.
But you could drop the proper condition, and if you consider only et al Lie groupoids, you drop the proper. Rather, you could drop the et al and put surjective summation, and you get Artin stacks. But you drop the proper condition and leave the et al condition, then what you get is something called a foliation groupoid, because more or less it is the same as the holonomy group of a foliation, groupoid of a foliation.
So we've seen something like that in this toric geometry.
That's right. In there the groupoids are et al, but not proper. And stabilizers are discrete, countable groups, discrete countable groups. And they are called foliation groupoids because they are the holonomy groupoids of foliations. So foliations generalize orbifolds. Orbifolds is a subcategory of foliations, and Artin stacks generalize orbifolds because now the stabilizers are compact Lie groups. So there are several generalizations of orbifolds, but it's often useful for me to start in the orbifold case, prove the theorems without worry. Often when you have the Artin situation, you need a little bit of analysis or something to account for the fact that now it's not finite groups. And often when you drop the proper condition, now you are in the universe of foliations, and now you need a little bit of dynamical systems or something to account for this situation. In any case, Bernardo Uribe and myself introduced a version of orbifold K-theory in the following manner. And only recently, a theorem either of Pardon or of Becerra and myself proved that this definition is really equivalent to all the definitions. But our definition was very simple, and people proposed more sophisticated definitions where the definition was nicer to prove that some general structural conditions about this theory, the functoriality properties, things like that. We propose this very simple-minded definition, and only all these years, after 20 years later, it turns out that they are equivalent to the more sophisticated definitions. But this took a long time to prove. And uses classical theorems of Graham-Segal in part of the proof, plus many other interesting things. In any case, let me do the easy definition, because I like it. We have a vector, because I'm in the search of cohomology, and it turns out that the cohomology that is easier to define for orbifolds is K-theory, not ordinary cohomology. Let me remind you that in classical topology, simplicial Homology and cohomology took a long time to develop at the beginning of the 20th century, culminating in the works of Lefschetz and Steenroth that clarified what simplicial cohomology and what it should be. And then all of a sudden, Grothendieck, Attila, and Hirzebruch discovered in the 60s, I believe, all the way down to the 60s or late 50s, maybe early 60s or middle 60s. I'm confused about those dates. But they discovered that there was another cohomology theory that had a very different definition, that was K theory. For ordinary topological spaces, this is surprisingly, K theory was very easy to define for compact spaces because it was just the so-called Grothendieck group completion of the monoid of vector bundles on the topological space. If I take a topological space, compact, then I consider all vector bundles, isomorphism class of vector bundles over the space, and I can add them so they form a monoid, or I don't know what you call them, a semi-group. And there is obviously the identity, that is the zero vector bundle. So it's a monoid or a semi-group, I don't know. And then you complete it, and this was K theory of X. And then you apply the same to the suspension of the space, you get K0 and K1. And it turns out that this was a cohomology theory. And Grothendieck discovered this in algebraic geometry, but it was Attila and Hirzebruch who noticed that this was a cohomology theory in the topological case, called topological K theory. It satisfied all the axioms of Eilenberg-MacLane for a cohomology theory. Surprisingly, it was striking when discovered. And except one, the K theory of a point was not just like the homology of a point. It was different. And it turns out that people started discovering Brown representability and all these things, that there were many cohomology theories, many, that they were in one-to-one correspondence with certain kind of so-called homotopy types of things called spectra. And I was very surprised. The whole thing was very surprising back in the 60s. But K theory is so nice, you know. It's I was enamored with K theory very early on in my career. Theorems that were exceedingly difficult using cohomology, that require, for example, secondary cohomology operations and things like that, were very easy in K theory. That was very natural from many points of view. In many ways, you could argue that K theory is the correct cohomology theory of the gods. Then there is many others, Morava K theories, elliptic cohomology, all the so-called chromatic hierarchy of cohomology theories. But K theory is something that is common. And in fact, there was this theorem early on that the K theory of a space tensor with the complex numbers was isomorphic to the cohomology of a space tensor with the complex numbers. Here I have to be careful about this isomorphism because this is only odd even graded, and this is integer graded, so I have to forget the integer grading and consider just the odd even grading. But this was also very surprised, and this was the culmination of the work of Chern and Hirzebruch, and is the Chern isomorphism using the Chern character, and the whole thing was very beautiful and still very beautiful. And of course, Bernardo and I were trying to copy this situation for orbifolds, so we decided to start with the development back at the beginning, just for compact orbifolds to define the theory. But this is only for compact spaces, what I just said. It turns out that defining K theory for non-compact spaces is more challenging. Today, you would just take the spectra and take blah, 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 and it's easier to do that. But back then, people were at the askings of how geometrically interpret this. And it turns out that elliptic operators parameterized over the space was the way to do it. And this led to all this incredible theory. So we wanted to revisit this development, but in the case of orbifolds, Graham Segal became famous for revisiting this development and making it an incredibly beautiful synthesis of the theory of representations of groups and K-theory. It turns out that K-theory, Graham Segal felt, I believe, uh, was like a representation of the space, representation theory of the space, uh, some sort of linearization of the space, in the words of Atiyah. And he made a great synthesis in the so-called, it's even today incredibly beautiful equivariant K theory of G acting on X for G, a group of enormous generality, a topological group. In particular, compiled groups and finite groups have nicer properties. And this was a synthesis between the classical theory of representation of groups and the newer theory at the time. This is the late 60s, of K theory of space. So this was a beautiful synthesis. The papers are a masterpiece of mathematics. And Graham Segal is himself extremely modest and good to tell me once, oh, I felt so embarrassed that I was making a career putting a G on the papers of my advisor. But this, of course, extremely unfair. This is a masterful synthesis of two worlds. In any case, we wanted to revisit Graham's development. Orbifolds look very much like groups acting on things, but it's now groupoids acting on things. If we go back to the concept of groupoid, in reality, this could be construed as X1, the groupoid. X1 could be the groupoid if you want. This would be the way that someone like Alan Kong would talk. X1 would be the groupoid, and it would be acting on X naught, the space. So it would be an action of X1 on X naught, a groupoid action of X1 on X naught. So we said, well, can we copy, can we plagiarize Graham and start the machine going for groupoid actions? You see what we tried to do back then?
Yes.
And so we did start copying the development, and we got some ways into this situation. And now we understand it much better after this theorem that Pardon on one hand and Becerra and myself proved recently on the other by different methods and on different levels of generality, very different methods. Anyway, we have this vector orbit bundle. We have this pair where it is an ordinary vector bundle over the space, and we have an isomorphism of vector bundles over X1, given by this isomorphism is given. So is this pair is a vector orbit bundle over X. So in 2004, we defined this Grothendieck group by K0 orb of X. And of course, there is a work of Adem and Ruan predating this work that we're trying to do it with charts. And in the case, but that kind of work was missing in this case. This case was not considered in the classical chart situation. And we wanted to include this case very importantly because we knew there were functors that sent an orbifold that, like normal classical orbifold, into this kind of thing. And we didn't want to lose that kind of thing because it was a natural thing. So this coincides with Graham Segal's equivariant K theory. If there is only one manifold acted on by one group, observe that a groupoid like this, if you have a classical group action, you can make this equal to M. You can make this equal to M cross G. And then a classical group action recovers the concept of, is a particular case of a Lie groupoid. And this definition recovers the definition of equivariant K theory of Graham Segal. in that case. But it's a more general situation. Perhaps I here should mention a theorem of Ike-Moerdijk that says that for any properly grouped point like this, and for any point in X0, and for any point, I lost, and for any point in X0, there is a neighborhood of X so that the restriction of the group point to this neighborhood looks like the action of a finite group on U. And this is called a slice of the group point. You see what I mean?
Yes.
So there is really a local orbifold chart. If you just give me a proper Lie group point and a point in the space X0 and a small neighborhood of X, the restriction of all the arrows that go from that neighborhood to that neighborhood is exactly U cross G. For G, a group that depends on X.
Okay.
In fact, G, the group that depends on X is the stabilizer of G, of X. So this is an orbifold chart. So this really captures the concept of an orbifold. There is all these local groups in this groupoid. Let me stop to see if you took that in. Is that okay, Misha?
Yes. So I think I get.
So we get these local orbifold charts. And so, well, we have that. And then recently, then Becerra and myself have proved by very different methods that that this orbifold K theory is if you allow G to be a compact Lie group, you may wonder whether you could be able to rewrite the orbifolds in this fashion. So let me explain this part. If I have a compact Lie group acting on a manifold, Kosul slice theorem says that for every point in the manifold, there exists a little, and say that you know that the stabilizer of every point is a finite group. Is finite. There is a theorem from 1954 that says that then there exists a little neighborhood of X so that the restriction of the action of G to M restricts to the action of GX to M. And so locally the quotient looks like an orbifold quotient. Locally, close to X. Looks just like a finite group acting on this finite group, the stabilizer, acting on a small neighborhood of the point. But this is not an open set of M. This is not an open set of M. It's a slice. It is inside of M, but it's not of the same dimension. It is of the dimension of the quotient. You see what I mean?
Yes.
It's a slice. It's called a slice. So it's Kosul slice theorem from 1954. And since 1954, we didn't know the converse. Is every orbifold obtained like the action of a compact Lie group on a manifold? We know an orbifold is not the action of a finite group on a manifold, because weighted projective space can be shown that is not of that form. You cannot get only one finite group acting on only one manifold that gives you weighted projective space. But weighted projective space, you know, is a quotient of a manifold by a compact Lie group, the circle. And so you would ask yourself, is there a converse? Is every orbifold of the form a manifold divided by a compact Lie group, not a finite group? And the answer is yes, and was only very recently obtained. Misha?
Could you tell a little bit more about how this result is obtained? So, is it something explicit? So you, out of this orbifold data, construct some either manifold and some group, or how it goes very roughly?
Well, it's very different proofs. Pardon's proof is by obstruction theory. So he shows that the obstruction to constructing this manifold and this group vanishes and it can be done. And, well, you could say that his proof is not constructive.
Exactly. So I'm wondering if it can be done explicitly.
But Serra and myself, we just construct the manifold and the group action. And that's how we prove it.
Mm-hmm. So I imagine in some sense this construction is functorial. So I don't know what exactly I mean by that, but in a sense, this is a very canonical thing.
Well, not really, because this is just another kind of atlas for the orbifold. So there is many of them.
Okay, so there are choices involved, and
yeah, lots of choices. Pardon kind of constructs some space, group action. He gives this very elaborate combinatorial procedure skeleton by skeleton, and he shows that at every step the obstruction doesn't permits you to continue with the construction. Our construction is so simple that it's transparent that there is no obstruction or anything. We just construct the example, and we construct something called the Mictilian action. Mictilian is a word in Nahuatl to denote something good and nice and beautiful. So we construct the Mictilian group action on the Mictilian manifold associated to the orbifold. We just construct the thing very explicitly. And pardon uses obstruction theory.
So I'm just wondering what happens if you vary the choices. So if you do some other choices in the construction, you get probably some other manifolds and some other groups acting on them. So how are they related?
Oh, this is known. They are related exactly by something called, it's a relation that was discovered by Ike Murdyk, and it's called a Morita equivalence.
Okay.
So there is an explicit equivalence relation between these actions, and this has been very explicitly written by Pronk and Scull, two Canadian mathematicians, I believe, and they very explicitly, Murdyk discovered the very general abstract relation, but Pronk and Scull has written very explicitly the equivalence relation between two of these group actions. And there is a very cute and nice proof of this by Andres Angel from Universidad de los Andes in Bogota, Colombia. He has a beautiful proof of the equivalence relation. And that is kind of but I can tell you more or less what it is. You want this to be equal to this. Well, you more or less want this to be equal to this. More or less, that's what it is. It's a category of fractions. You see what I mean?
No, not really.
Well, you want this, you more or less want this.
Yes.
And you just carry this out in the categorical framework. That is what it is.
Yeah, but that sounds not very explicit.
I can explain it if I can go full explicit about that subject in another talk.
Yeah, I would love to. I would
could
love to
talk
hear
about
that.
our proof and
Yes.
this relation. I could do that, But of course, this was open since 1954, and now almost simultaneously. In fact, we obtained our proof almost simultaneously, pardon published earlier, because we were confused about something, but our proof is also correct. It's very different. So I don't know if you want me to continue or we continue next time.
So for me, it's okay. I can listen, but for Nikita, might be already kind of late.
A little bit late. Yeah, I guess it's it is
just midnight.
Let me do 10 more minutes and then I'll drop it.
Okay, then 10 minutes is fine.
Mm-hmm. So, if you have a Riemannian metric, you have a family of canonically defined elliptic operators, the Laplacian on K forms. And these are related to a quantum field theory, and a quantum field theory has fields. This sentence is wrong, but the fields in this quantum field theory are sort of strings in the sense that they are maps from intervals or the circle to M. These are the fields of the theory, of the quantum field theory. And so you get one of these fields, say it is a map from the circle to M, you give it a Lagrangian, you have one of the fields and you want a Lagrangian on the field and you want to get the stationary points of the Lagrangian, the Euler-Lagrange equation associated to the Lagrangian. But anyway, the Lagrangian will just be, I will assume that we have a Riemannian metric and that this makes sense. And this produces a theory. Once I give you a Lagrangian, you just go off with the machine of quantum field theory and produce a quantum field theory associated to the Lagrangian. This is a very simple quantum field theory. Physicists would laugh at you. And all the spectrum of these is related to these. This is related to this because the information of this quantum theory and the evolution and everything is contained. Sort of the Hamiltonian for this theory is given that I use the derivative here, is this the spectrum of the Laplacian. So recovering the classical theory, that is to say the manifold M, from the quantum theory, the spectrum of the Laplacian, is here in the shape of the drum. You probably have heard this expression, haven't you?
Yes.
So this is trying to recover the classical world from the quantum world. But because information is destroyed passing from the classical to the quantum, well, this is not always possible. Sometimes it is, surprisingly. The Feynman functional integration approach for the theory allows to compute an integral over the three-loop space of the manifold by a stationary phase approximation. Well, There is a heat kernel approach that I will go about next time. And I will explain a little bit of the heat kernel approach and how this recovers the Gauss-Bonnet theorem. I will try to explain this next time. And how we could recover by one such field theory the Atiyah-Singer index theorem. But then what I will do next time is to apply the same scheme, the same story that is very related to K-theory. We know that because of the theorem of the work of Atiyah, Singer, and Siegel in the equivariant case. Interestingly, the non-equivariant case was only originally proved by use of the equivariant case. You cannot do one without the other. But in any case, well, what did we do? We revisited this story, defining the loop space of an orbifold. But of course, the loop orbifold of an orbifold is not a space. It's a orbifold itself. If it's a category, the loop category of the categories is a category. And orbifolds are categories, are groupoids. So we had to define this functor that, given this groupoid, gave me a groupoid that took the place of the loop space. And then we revisited this quantum field theory approach to the index of elliptic operators that are the natural objects for K-theory in the non-compact case. This is the subject of the talk next time. And for now, this is all. Thank you very much.
Thank you so much. So, yeah, I'm looking forward to hear the continuation.